Yes, please, Monique, the floor is yours.
Yes, it's my great pleasure to introduce John Asbury. He got his PhD in 2001 from Emory University, after which he went to Michael Feyer's group in Stanford University to be a postdoc there till 2005. And ever since, he has been a faculty member at Pennsylvania State University, being promoted to full professor in 2019. Among many prestigious awards, he has received the US Department of Energy Career Award and the NSF Career Award as well. He works on, well, what I like personally the most in his work is that he does a lot of very advanced infrared spectroscopy and does methodology development there. And he applies that to a series of advanced materials and photovoltaics, amongst others. So, John, by this, the floor is yours.
Thank you, Monique and Laura. I really appreciate the opportunity to join you. This is, of course, this format is unique in many respects, but being able to cross the Atlantic by wire as opposed to in person makes these conversations more much easier. I'm going to share my screen and get us started this afternoon, your time. And let's see, enter that full screen mode and pull up my laser pointer, virtual laser pointer. Yes. Right, so as Monica indicated, my group, sort of our special sauce, if you will, is developing ultrafast infrared methods to examine electronic processes and materials. And as we'll see today, the reason we do this is we're interested in trying to understand how the structure, molecular crystal structure of materials gives rise to their electronic properties, and to develop design rules to know how to tune them. And a big part of that is just being able to correlate the structure with those properties. And the infrared allows us to do that in ways that are unique in comparison to what you can do with traditional electronic spectroscopies. And so we do electronic spectroscopy, but we always like to focus on the infrared to provide that unique information. Let me set a context for why we are interested in the things we are interested in. And then also to kind of build up a framework so we can understand where the opportunities lie. All of the materials we examine in my group are related to energy materials, whether they are photovoltaic materials, as context of today, photocatalytic materials, which will appear later in the talk today, or traditional, new directions are in traditional electrocatalysis, where we're using ultrafast methods to look at chemical intermediates. This is a picture in the lower left of, I just pulled it from a Google Images search, but it conveys the issue that I want to address, that we want to address. You have in the you have the lower right of the picture, you have a few megawatt photovoltaic array with silicon. You have a few megawatt wind farm that I cropped is over here. But the heavy lifting is done by this few gigawatt coal-fired power plant, right? And that sort of encapsulates the problem that we have, which is silicon, for example, is a wonderful technology. You know, you can put these panels on your roof and they'll last as longer than your roof. You have to remove them to replace the roof and put them back. But making enough of them to have provide a significant fraction of the total energy economy globally is a very daunting task. We are orders of magnitude away from the production capacity needed to do that. And one of the issues is that silicon is a very mature technology. So, if you just install a system on your roof, only a third of that cost is actually the panels. Most of it is just inverters and the infrastructure to hold it up there. And this is a very mature technology. It's already at over 80% of the theoretical power conversion efficiency. And whenever you have a technology at that level, it's not going to change very much from where its status. And you can see that in the history of the efficiency of silicon panels over the past 20 years. It's been the same. So I'd like to look at, take a dive into the physics of photovoltaics, not just silicon, to identify where some opportunities are, and then discuss some contemporary research work to address those. So to do that, let's just kind of begin with some basics. I think most of us will be aware that silicon is a semiconductor with a valence and a conduction band. Valence band being occupied in the ground state. Absorption of light excites electron to the conduction band, causing it to be conductive. Those charges, the whole positive charge hole in the valence band, electron in the conduction band, would have no preferred direction and therefore would not make current unless you give them a gradient to follow, and that's done typically by doping the semiconductor to create the static electric field at the junction. And doping occurs by replace a few of the silicon atoms with boron, for example, and you have an atom with 3 valence electrons and a lattice that wants to have 4 bonds, and it makes it very easy to add the 4th electron. From an energy level perspective, we would think about that as having a Fermi level that was very close to the valence band edge, because it's easy to add electrons. The material wants to grab an electron to fulfill the 4 bonds of the tetrahedral bonding geometry. N-type doping occurs. We replace a few silicon atoms with phosphorus. You're adding an atom with an extra valence electron. It makes it easy to remove that 5th electron, valence electron. And the equivalent is a Fermi level that is close to the conduction band, where the Fermi level describes the centroid of the thermal distribution of the highest energy electrons. I should just be clear on that point. Now, when you make a junction between these two materials, you'll have electrons flow from the N-type to the P-type in order to create a continuous variation in that Fermi level across the junction. And that flow of charge creates the static electric field that then gives preferred direction to charge transport, and therefore current collection in the device. Okay, now looking at the electronic properties of ideal semiconductor as a photovoltaic, the current is going to come from absorption of photons. Each photon will create 1 electron hole pair generally, unless you do something special, which we'll talk about. The voltage of a solar cell is actually coming. It's not coming from the valence and conduction band edges, although it's related to them. It's coming from what we call a quasi-Fermi level, which is the energetic related to the energetic distribution of electrons that are created in the conduction band and holes that are left behind in the valence band. These create thermal distributions, and you can describe those with a Boltzmann distribution of states, occupied states, and the energies corresponding to the distribution of electrons and holes represent these what we call quasi-Fermi levels, and it's the energy difference between those levels that determines the operating voltage of the solar cell. So if you have current generation from your absorption of your sunlight, you're going to have some recombination losses that, in the absence of current, would match the current generation. If you allow current to flow, then you can build up a steady state distribution of electrons and holes, and that just the higher the density of electrons and holes, the closer the quasi-Fermi levels are to the band edges. They will be pinned by the band edges because the density of states will increase very, very rapidly at those edges. And that's why it gets pinned there. Okay. Now, in a ideal photovoltaic, you would turn on some light and you get the maximum voltage that the cell can produce, and then as you increase the voltage, so if you have a small voltage, you'll get a certain current, and you can allow the cell to push against a voltage up to the maximum VOC, and ideally you'd have the same current throughout until it just collapsed, because you are now trying to have it push current against a potential greater than its maximum. What you actually see is a current curve that looks like this, where you turn on the light, you increase the voltage that the cell has to push against to get more power from it, and the current drops. And you, of course, the real cell has some operating maximum power point here, where we basically have the maximum current voltage product. And I use an analogy of a leaky dam to sort of illustrate what's going on here. So, in a hydroelectric power generation plant, you have the current of the solar cells replaced by water flow through the dam, and that's related to it's limited by the rainfall. If you keep the water level low in the dam, you'll have the same water flow, just not very much pressure, and that will result in low power. So of course you increase the water column in the dam, and you get more pressure flow through the hydroelectric plant, and you maximize the power. And this is the equivalent to the ideal semiconductor. A leaky dam, however, would have a power curve like this, where if you keep a low water column, right, you have the flow limited by rain, just as before, but you don't have very many leaks that are accessible by the water level. But as you increase the water column to increase the pressure, what happens is you have more leaks, and you lose water through the leaks, and so you have to therefore reduce the flow through the dam, and the result is you have a curve that looks like that. So a leaky dam is the equivalent to the recombination losses in a real photovoltaic device. Okay, and as I mentioned, silicon is already it's at this theoretical efficiency. Let's just review why the theoretical efficiency is what it is, which is about 30%. So 30% theoretical efficiency means you have about a 70% loss. About half of that loss is due to the fact that the sun spectrum is very broad, so it's distributed. Silicon has a band gap of about 1.1 electron volts, which corresponds to 1100 nanometers in wavelength. And so any photon with energy greater than that will be absorbed, or can be absorbed. But because silicon is a bulk semiconductor, and this excess energy above the band gap is very rapidly lost due to a process called electron phonon scattering. Phonons are just the collective vibrations of the silicon lattice, and those vibrations can couple to the electronic states and allow for very rapid heat loss, energy loss, on the order of 100 femtoseconds, typically for a bulk semiconductor like this. And so that loss of energy corresponds to about half of this 70% theoretical 70% loss of energy. And the result is you have a maximum, you can vary the band gap of the material and predict what the theoretical efficiency of the device will be. And it peaks up a little over 30%, where if you increase the band gap beyond the optimal level, you can retain a lot of energy or high energy photons, but you just don't absorb very many photons. If you're below that level, you can absorb lots of photons, but you retain very little energy of any of them, and the consequence is that there's a happy medium in the middle. Okay, so that background kind of gives us a context. Think about the efforts that have been employed to go beyond this 30-ish% power conversion efficiency. One of those is solar concentration, as this upper left figure indicates. If you concentrate sunlight just by having a system of reflectors, you can actually increase the efficiency of your photovoltaic cell because you take advantage of these quasi-Fermi levels. You can have a higher generation rate. The recombination rate is going to be a characteristic of the material, means you can push these quasi-Fermi levels closer to the band edges, and as a consequence, you have a higher operating voltage of your solar cell. Of course, you can also use much smaller solar cells, because the cell is actually in this little collector here, and so you can use very high quality, expensive materials and have a very efficient device. The challenge, of course, is you have to move the thing because the sun moves. So it's high maintenance. You can also create a multi-junction cell, and that's typically done in space applications, because you're not so worried about cost, where you can have a high energy, high band gap layer that absorbs the high energy photons and transmits the lower energy ones, and then another layer that absorbs the medium, and another layer absorbs the longer wavelength ones. And you can preserve more of the energy that way, minimizing these heat losses, and harvest more of the energy from the solar spectrum. Another approach that is hopefully more useful for terrestrial applications, because both of these are expensive, is that you could potentially undergo multi-exciton generation. This is an idea that's been around for some time, where instead of, if you design the material correctly, you could use the energy of a high energy photon to excite another electron hole pair in the material and multiply the current that's generated from high energy photons. And if you designed a layer that would essentially sensitize, say, a silicon photovoltaic, as my little cartoon's trying to indicate a film that you could peel off and put back on, that would create the extra excitons, that would allow you to have a very efficient device for essentially the same cost and structure as a silicon. And so that's sort of the opportunity to think about here. For some time, quantum dots were, a quantum dot is a small nanocrystal whose dimension is smaller than the Bohr radius of the exciton. So just as a quick background, we describe an exciton as an electron hole pair, where the hole is imagined like the nucleus of a hydrogen atom. The electron is an electron. And so you could describe that pair as you would a hydrogen atom. You have hydrogenic states. And just as a hydrogen atom is a Bohr radius, the characteristic diameter or radius of the wave functions. And if the nanocrystal is smaller than that characteristic size of the wave functions of the exciton, then it becomes quantum confined and it acts like a particle in a box. And so that quantum confinement causes energy levels between, picture a 1s, 1s, 2s, 3s, or because of changes in the symmetry, you have opportunities to have 1s, 1p, and 1d, which are not permitted in an actual hydrogen atom. These states, the energy difference between these states increases with the quantum confinement. And the idea was that, oh, wow, this would allow you to, what the term was called a Phonon Bottleneck, where you could potentially slow energy relaxation between the levels, because you had to conserve energy. So the energy had to flow into phonons, and the bigger differences there are between the states, the more phonons had to be excited at any one time. And as a consequence, the expectation was that the energy would slow down and you would have more time for this multi-exciton generation process to occur. Unfortunately, that was not observed. And so there's been a number of efforts in metal chalcogenides, the metals chalcogenides being like sulfur and selenium, to understand why and can you overcome this problem, to show you that this phonon bottleneck or slowing of relaxation has not been observed as expected. You can explore the relaxation process measured. These are from transient absorption measurements in the visible in these is cadmium selenide materials, and the larger nanocrystals, which have less energy, smaller energy gaps, actually have slower relaxation. Smaller nanocrystals with bigger energy gaps actually have faster relaxation. And so that's counterintuitive. In cadmium selenide, the explanation was found through was an Auger relaxation mechanism. I'll just replay this. If you excite a high energy with a high energy photon, the excess energy of the electron can actually be transferred to the hole. And in cadmium selenide, for example, the effective mass of the hole, which determines the size of the wave functions, is larger. So wave functions are the diameter, or the size of the wave functions of the hole is smaller, and therefore energy states are closer together. So if you transfer the energy of the electron into the hole, it allows for fast relaxation and overcoming this bottleneck. But the lead chalcogenides, sulfur, selenium, are chalcogenides again, the effective masses of electrons in holes are almost the same. So that's not the explanation, and yet the phonon bottleneck remains to be observed in these materials. It has been observed if you grow an onion, that is to say, take a lead selenide nanocrystal and you grow enough layers that you can electronically isolate the core from everything around it. You can actually observe very slow relaxation. Philippe Guillot demonstrated this some years ago. But such materials are not useful for optoelectronic applications because the electrons and holes are trapped inside the onion. And so we wish to find a way around this that doesn't require growing onions. There have been a number of explanations for the lead chalcogenides. A popular one is that, well, it's the vibrations of the ligands that couple to the electronic states of the nanocrystal, and the energy is actually, it's not the low frequency phonons of the inorganic lattice, it's the high frequency vibrations of the ligands, which requires fewer, the energy flow through the ligands would require fewer quanta of those vibrations, and that must be where the energy is flowing. That's been a popular thought. Other ideas have been explored, thinking about coupling to surface or potentially bulk phonons. And so we're going to explore that. I should note that there have been some suggestions in the literature that this picture of the quantum dot with my little simplified energy levels is just not correct. And that's why you don't observe the phonon bottleneck. That the density of states aren't actually discrete, that they overlap. This is a density of states suggested by Oleg Brezhnev. David Jonas noted some years ago what he called bulk-like hot carrier dynamics in lead sulfide. Frank Weiss actually early on, suggested, well, this is our ideal. Does the electronic structure actually look like this? And what I'll show you in a little bit is that we're going to replace this cartoon with data, and we'll show you that this is actually the lower figure here that Frank Weiss suggested is actually what these nanocrystals look like. So let's show you. I'll show you how we got there. Okay, so as was mentioned at the beginning, we do a lot of things in the infrared, and so this is the infrared spectrum plotted in electron volt scale. So just for reference, this is about 1,200 wave numbers. If you're familiar with that unit, 1,200 wave numbers to about 5,000 wave numbers, and then this is electronic region. This is about 700 nanometers wavelength. Okay, now we're looking at lead sulfide nanocrystals in a dense film, so there's no solvent in this particular on the left-hand side. The nanocrystals are surrounded by ligands. We have several types of ligands that we're going to look at. We're going to excite the band gaps of these nanocrystals, and we're going to probe it really in the mid-infrared through the visible also, but we'll just do the whole range. This is the work that we did in collaboration with Matt Beard at the National Renewable Energy Lab. His former student, Ashley Marshall, made the nanocrystals. I should say my former student, Eric Kinahan, made the measurements. So we have several transitions here, and this is a figure I actually used when just introducing transient absorption spectroscopy, because you have so many types of transitions represented here. This negative going transition is we call it the bleach, or reduction of the ground state absorption that results because we're exciting the film. This corresponds to the excitonic band gap. And the black transition is sort of indicating the bleaching of that transition. The red here is what's known as the 1s to 1p. So these are these quantum confined states of the hydrogenic states. And due to the different selection rules, you can have different angular momentum states of the n=1 solution. So the lower energy transition is this 1s to 1p. This is actually, I'll show you the 1s to 1d, which is formally symmetry forbidden, but because these are nanocrystals, they actually break the symmetry, and that becomes weakly allowed. We also, not in this figure, but measured the photoluminescence, just emission of the nanocrystals. That's in this aqua color, and all of the kinetics traces are plotted on top of each other and are in quantitative agreement, indicating that all the transitions arise from the same electronic state, the excitonic state of the nanocrystal. Importantly, they tell us that this region of the spectrum is not result from trapping. It does not result from mid-gap states or defects. It's actually just an optical transition of the exciton. That's a little bit different. It's a little unusual to see that. These are just really very electronically high-quality materials from Matt's group. If we look at these broad electronic spectra from the infrared into the visible for different sizes of nanocrystals, okay, you can see the excitonic transitions vary with size, as do the 1s to 1p transitions and the 1s to 1d. Note color coding the different transitions here. We can predict from the band gap where the 1s to 1p and the 1s to 1d transition energies should lie. These are the lines calculated here, and they fall within quantitative, within experimental precision with the measured energies of these log normal line shape functions, which is characteristic for this type of transition. The note about the oscillator strength of this 1s to 1d transition, which as I said, is formally forbidden by symmetry. You can see as a function of size the evidence of what we call oscillator strength borrowing. So that's a characteristic of a transition that is has some for some reason is borrowing oscillator strength from an allowed transition. In this case, the allowed transition is the 1s to 1p. By breaking symmetry of the nanocrystals, the 1s to 1d transition becomes weakly allowed, and the break of symmetry also makes the 1s to 1p slightly less allowed. And so what you see is that as you move to smaller nanocrystals, who have a larger inverse volume, is what's plotted here, you see weaker 1s to 1p transitions and stronger 1s to 1d transitions. The origin of the symmetry break is simply that you have a sulfur and a lead sublattice in the nanocrystal, and they don't match exactly the envelope of the whole nanocrystal, and that breaks the spherical symmetry, which is the symmetry that leads to the forbidden 1s to 1d transition. So just by the shape of the nanocrystals. The width of these peaks, size variation is this power law function, which is indicative of a broadening due to electron phonon coupling, much in the way you think of broadening in a molecular electronic spectra, where you have basically displacements of your nuclear configurations for your ground versus excited states. The same thing is happening in these nanocrystals, and that gets much stronger as the nanocrystal gets smaller, as you might expect. What we can do now with these spectra is, because we're measuring the full spectral range of electronic transitions with high fidelity, we can actually fit them, as the line shapes here in color-coded form indicate. But that allows us to then take from these experimental spectra and effectively create energy level and energy diagram for the different transitions of the nanocrystals for different sizes. So that's what I have on the lower part of the slide here. And so what we're doing now is we're considering that we're thinking about the energy of the 1p versus the 1d state relative to the excitonic excited state, which we're going to call the zero of energy is for all of these nanocrystals is the center of the excitonic transition. So we just basically take the line shape function used to fit this spectra, and we're going to just map that onto an energy diagram here. Do that for all the different sizes, and you can see that here. Do the same thing for this 1p transition is the excitonic energy plus the energy to go up to 1p. And so the transition energy just maps onto an energy diagram, and you do the same for the 1d. You see that there. And what I want to emphasize here is that these line shapes are quite broad, and the breadth increases rapidly with decreasing nanocrystal size, so that for the smallest nanocrystals, you actually have overlap of the energetic distribution of your 1p state and even your 1d state with your excitonic state. The red here shows you overlap of this 1d energy distribution versus the 1s versus the excitonic. What it tells you is that there is a resonant relaxation channel, meaning you can conserve energy, going from from a 1d state to a 1s state without having to excite any additional phonons, just the phonons that are coupled to the electronic transition by the nature of the quantum confinement of the nanocrystal and the softness of the lattice, basically. This is why you don't see phonon bottleneck in the metal chalcogenides, because you don't have to excite phonons of the lattice that aren't already excited by the electronic transition itself. Okay, so that's we'd like to explore the origin of the phonons coupling to that electronic transition, because that would give us some insight about how to solve this problem. I would note, however, before I do that, that we can now replace Frank Wise's cartoon with data and show this is what the electronic density of states of these nanocrystals actually looks like. Of course, when you have larger nanocrystals, the electron phonon coupling weakens corresponding because of the less localization of the wave functions, and these lines narrow, and you get more like this ideal shape, and that's why you can actually see longer. The phonon bottleneck actually persists longer in the larger nanocrystals because you're turning off these resonant relaxation channels. Okay, now let's explore the origin of those phonons. So as I mentioned, some popular thoughts were that it's either the ligands attached to the nanocrystals are providing a high energy phonons effectively to relax into, or maybe the surface phonons. We've sort of excluded the bulk because the relaxation processes we're observing here don't vary a lot. With the electron phonon coupling has well, let me say I'll show you that it's not size dependent. So we're gonna focus on either the surface phonons or the vibrations of the ligands. To do that, we're going to look at these electronic spectra again. This is for the larger nanocrystals, so you see low energy 1s to 1p transitions here. And I'm going to focus on this gray box, which looks like there's some noise there. But if you zoom in on that with a higher resolution spectrum, you realize that noise is not noise. It's actually the vibrational features of the ligands that are attached to the lead sulfide nanocrystals. So we're looking in the region where the carboxylate groups, so carboxylate functional group is a common anchoring group for ligands on metal chalcogenide nanocrystals. And carboxylates, that I'll show you, have some beautiful infrared spectra that allow you to probe their surface chemistry in ice waves. So I'll show you. If we take this is just this is a repeat of the spectrum I showed you for the larger nanocrystals, and there's just the same spectra for the other nanocrystal sizes we've explored. If you just take the curvature of these shapes and color code them for positive versus negative, and then fit this electronic transition, which is related to this 1s to 1p transition, we can subtract that, remove it, and isolate the transient vibrational spectra of the ligands attached to the nanocrystal surfaces. I'll show you that in a moment. Let me just mention here. This is a ground state absorption spectrum of the nanocrystal films in the region of the carboxylate. This is the carboxylate group, where that group absorbs. And it turns out that there are characteristic frequency differences between if you can see in my picture, the symmetric carboxylate stretch versus the antisymmetric stretch. They have different frequencies, and those the frequency differences are sensitive to the type of bonding that the carboxylate groups are making to the surface. So this is known from looking at various acetate salt crystals, and this is looking at the X-ray diffraction measurements of their structure and infrared absorption measurements of their spectra. So if your oxygens of your carboxylate groups are bonded to the same atom, the frequency difference between the symmetric and antisymmetric stretches will be smallest, around 100 wave numbers. If they're bridging two neighboring sites, the difference will be a little bit bigger. And then if you have this unidentate, where only one oxygen is really bonded and the other one is more of a formal carbon-oxygen double bond, then the frequency difference will be much, much larger. And so you can see in these spectra, there are pairs of lines that are closest together. This is a CH bend, I'm sorry, so we'll ignore that. The reddish lines indicate the chelating geometry. This one, the blue lines indicate the bridging geometry. The top one, there's negligible amount of this unidentate form in the films we're examining here, but they will appear in the transient spectra, which I'll show you now. So these spectra result from doing the subtraction I mentioned, where we're going to remove the slowly varying electronic baseline and just isolate the transient vibrational spectra for different nanocrystal sizes. The negative here is indicative of loss of the ground state structure and its corresponding absorption. The positive is the product that's forming in the excited state. And so what you're seeing is this reduction of the chelating most bonding geometry, an increase in the bridging structure, and the formation of this unidentator, I guess I'm calling it monodentator on this slide for some reason, bonding geometry. So what if you just analyzing the patterns in these vibrational spectra, the ground state, as I mentioned on the previous slide, is dominated by these two bonding forms. And in the excited state, we're losing the chelating and retaining the bridging. And I'll show you why it's enhanced in a minute. And we're also gaining this monodentate. So if you think about the average lead-oxygen bonding, you're seeing a net reduction in the lead-oxygen coordination in the excited state of the nanocrystals. Now, this has some important implications for using these nanocrystals for photocatalysis, because in a photocatalytic process, you want to use the energy of the exciton, or maybe use the electron that's excited to drive a reaction. That means you got to bring something close to the surface of the nanocrystal to receive that electron. The bonding of the ligands to the surface will limit their ability to create open transient spaces for other molecular species to come close to the surface to either receive the electron or undergo a bond rearrangement. But we're seeing that the ligand binding is actually weakening in the excited state. And so that's an interesting, that's certainly in the right direction if you're trying to do a photocatalytic reaction. And we're interested in exploring how that mediates catalytic processes that occur on such nanocrystal surfaces. So we're interested to explore that. But I want to sort of continue the theme of the phonon bottleneck question here by showing you. We focused on the carboxylate groups of they were oleate ligands, which were the long chain ligands. Here we're looking at we've done the same kind of spectroscopy I've described, but we switched the ligand from the oleates with the carboxylate only to a mercaptopropionic acid, which has a thiol and a carboxylate. We're still probing the carboxylate, but these molecules are also bound by the thiol. And what we see in the transient vibrational spectra of these samples looks different than the oleate capped nanocrystals. What you see is more like a Stark shift or a shift of the vibrational frequency. They all seem to shift to lower frequencies, which is characteristic of such a stark shift, and would be consistent, for example, with trapping a charge. In this case, picturing an electron at the surface, which would just change the charge distribution at the surface and give you a vibrational stark shift. There's not the evidence of the reorganization of the surface chemistry that we saw for just oleate. And we imagine the reason for this is that the ligand is anchored in two places, essentially on both ends, and as a consequence, any transient perturbation of the carboxylate will be short-lived because the anchor of the sulfur keeps it in the same place, and it can simply rebind in the same configuration. What I would like to emphasize here is that we have two ligand chemistries that are quite different from each other. Oleates versus this thiol and carboxylate mixtures. The line shapes that we observe in these transient spectra of the electronic manifold now, we're returning back to the 1s to 1p transition and noting the electron phonon coupling that gives rise to the breadth of the peaks. It's essentially the same for both types of ligands. And that indicates that the ligand vibrations don't seem to have much impact on the phonons that are coupling to the electronic transition, giving rise to this the breadth of these transitions. And what that suggests to us, and I'll show you in a second that it's true, it suggests to us that the ligands themselves are not providing the phonons that are coupling to the electronic transition, giving rise to these resonant relaxation paths that I discussed in the first part of this talk. And just to see that's true, if we look at, we can excite nanocrystals with higher energy photons, just a green 532 nanometer photon, and we can probe the relaxation of the excitonic state by the growth of the 1s to 1p transition, where initially it's small because your excited states are not the lowest energy excitonic state, they're actually the 1d state. And then as the relaxation occurs, you'll see a growth in this 1s to 1p transition, and that growth kinetics is plotted here on this graph in the largest nanocrystals for both the oleate and the mercaptogroupionic acid, actually with iodide mixtures, and those kinetics are essentially identical to each other. Now, just to show that when there are differences, you can measure them. If you measure the smaller nanocrystals with this, this is done with the mercaptogroupionic acid. The smaller nanocrystals have observed by others to undergo faster relaxation, and we observe the same thing. And so this is indicating that when there are differences, we can measure them. There are not differences in these relaxation channels due to changing the vibrational structure or chemical identity of the ligands. And as a consequence, conclude that it's not the ligands that are causing this electron-phonon coupling, it's rather the nanocrystal surfaces. And it's the perturbation of those surfaces, we believe, that's actually giving rise to the change in bonding of the carboxylates. Just for a quick bit of photophysics here, I would just note this significant amplification of the bridging as actually the symmetric stretch of the bridging vibrational mode. And that, as it turns out, is related to the interaction of the carboxylate group with its image transition dipole in the polarizable excitonic state. If this was a metal, it would be a true image dipole. What you have is rather a polarization of the exciton rather than a charge distribution. But I'll discuss it in terms of a metal because it's easy to think about. If I put a dipole, if I have a surface and I put a dipole facing normal to the surface, it will polarize the electron distribution below that surface and create the image dipole of that. If I have a transition dipole, it'll do the same thing. It'll create a transition dipole, an oscillating dipole that follows the same thing. And that enhances the symmetric stretch, but it actually suppresses the anti-symmetric stretch, which is higher frequency, because the image dipole is an opposite to for a dipole that's, so the symmetric stretch, you realize the symmetric stretch, the transition dipole is normal to the surface. Anti-symmetric stretch, the transition dipole is parallel to the surface. And the parallel dipole is canceled by its image dipole, and therefore that suppresses the anti-symmetric stretch there. Okay, let me see. So in terms of conclusions from this part of from this work, we've identified that the vibrational modes of the ligands are not the source of the phonons coupling to the electronic transition, that it is the phonon modes of the nanocrystals themselves. We believe they are on the surfaces of the nanocrystals. Ways if you think about how do you design nanocrystals that permit the electronic communication with their surroundings for photovoltaic or photocatalytic applications, while also restraining these phonons to limit this coupling. Some things that of course core shell structures have long been explored in the community, although a more recent exploration of what we would call graded surface nanostructures, where instead of having a sharp interface between the core and the shell, you have a graduation of the you essentially have an alloy going from the core into the shell, and thus softening the interface is as a potential pathway to allow this communication that you need, while also essentially better defining that surface. And because one of the problems with surface phonons is the surface is disordered, and the phonon spectrum is therefore very broad, which is certainly bad for having such coupling. So these are some things that we're thinking about. That's in terms of what the next steps are for these types of materials. I need to say something. I'm required by Penn State to acknowledge I have a conflict of interest. A number of the measurements that I discussed were enabled by operating with very low excitation intensities, so we could really avoid nonlinear effects. That kind of thing was only recently made possible by some innovations in the group. We commercialized them. I have a company, and the company benefits financially when people want to buy those things. So that I have to do. That's my disclosure. Okay. So with that, this work was supported by the Department of Energy, and that was much of that was the thesis work of Eric Kinahan, who's actually now leading Magnitude Instruments. I'd like to thank everyone for their attention, and we'll be happy to answer any questions if we have time.
Thank you very much for this wonderful talk, John. Yeah, we generally don't hear the applause online, but I'm sure it's there.
Thank you.
Atsushi is really making an effort. So the floor is open for questions. Would like to go first?
I can open the chat too.
I think Arjan unmuted himself.
That was so that I could clap and he could hear the applause. But I do have a few questions. I just didn't want to go first necessarily. So if anybody else wants to go first, then I'm happy to wait a while.
No, Arjan, please go ahead.
I will go then. Yeah, thank you very much, John. Very, very impressive talk. I really enjoyed how you extracted the information from the vibrational information, basically, on top of your intraband transition curve. I'm not sure if you are aware, but I have a group here in Delft, and we have done a lot of cooling spectroscopy, especially on lead selenide. So I've thought about these in Phonon Bottlenecks. And I have to say, we have the same experience, that we thought that exchanging ligands would help. It did not. So in that sense, that seems to line up. Yeah. I had a question on the line shape of the P and D states. It seems to be that those line shapes are a lot broader than of the S states. And I wonder if you can understand that in the context of surface phonon coupling.
Let's see, let me just go to, yeah, they are much broader. Yeah, so if you look at the variance of these log normal functions, for the S state, it's very small. It doesn't hardly shows up on the scale, whereas the 1P and 1D states are much, much higher. So that's a good question. I'm trying to think the origin of the how these states would be affected by this coupling to the phonons and be so differently. To be honest, it's been a while since I've thought about that question, and so I'm having to sort of access memories from a couple of years ago, which is always a little bit of a dangerous task to do it on the fly.
Maybe a related discussion, because that was maybe an explanation I was thinking about, is that these are, of course, ensemble measurements, right? And you are not discussing so much size and shape variation of the particles, how they could affect the width of these line shapes. And I would think that P and D states are more susceptible to size and especially shape variations than S states. So could that play a role? That these are not homogeneous line shapes, but inhomogeneous line shapes?
We don't have a separate, these are not photon echo measurements, and so we don't have a separate measure of the homogeneous versus the heterogeneous contributions. The other thing I would note is that the excitonic transitions are they're fairly narrow and much narrower than these line shapes, and so but your question was,
so that
might the 1s to 1d transition be more sensitive to
so the P level variation? Of course, the P level, the orbital is less symmetric, right? So if you have some shape variations, it's going to affect much more the P states.
Fit into that. That's an interesting question.
I think you see it in general that the P levels are broader than S levels. Whether or not that translates into electron phonon coupling, I don't know.
That's an interesting question. I hadn't considered that the change in symmetry of the orbital itself would affect how it samples an irregular shape in the nanocrystal. But I am going to think about that some more. That's an excellent suggestion.
I'm waiting for somebody else to ask a question. If not, I have another one. Shall I just go until somebody stops me? I was very triggered by this change of the bidentate to monodentate binding of the carboxylate on the surface. And I was trying to think if I could envision how an excitation of the nanocrystal, and so having probably an S-type electronic state, could ever trigger this. So can we see this as a chemical reaction, and can we understand why one of the leads would let go of the oxygen?
Yeah.
You have a picture of that?
Well, so my thinking here was that if we think about phonons of the nanocrystal being those that are excited by the electronic transition, those on the surface would if you to oversimplify, if you think about my fingers are the surface atoms, and if I'm exciting surface phonons and I'm increasing the vibrational energy of those of the surface, those surfaces are coupled, of course, to the carboxylates because they're bonded to each other, and that could give rise to weakening of the bonding of
it's like thermal then. It's like thermal breaking of one of the bonds.
So that's been my thinking about it. I don't know. It certainly could be electronic. I mean, I don't know if it has an electronic component that is just simply changing, going into an excited state. And potentially even a state that has a different symmetry than the S state, that could change. That could affect that. I don't know.
We also think a lot about, let's say, trapping events on the surface as if that is an electrochemical reaction. And so things we see in DFT calculations and some electrochemical experiments is that you can have local reduction of lead ions on the surface. In cadmium selenide, it's much clearer, but also in lead selenide or sulfide. I could imagine that you somehow start to reduce that bond or the lead ion and then breaking the bond. But I'm not sure if that is at all what is happening. That could be another picture that's more chemical in nature, that you localize the electron somewhere nearby, hence breaking the chemical bond there.
This is sort of our thinking in the mercaptor propionic acid one. And it could be occurring in the oleic acid case as well, and just simply the ligands respond a little bit differently because they're not anchored by two different, anchored at 2 points. That certainly is a possible origin.
Is that monodentate binding, is it long-lived? Because I suppose you show transient spectra at a certain time delay. And
it is long-lived. So these spectra are actually measured at 30 nanoseconds. So yeah, it's thermalized. It's just and if it was a transient, sort of a perturbation and then have time to reform, I would expect it to have reformed by 30 nanoseconds. And if we can probe this longer, and you basically just, the signals stay the same, they just get smaller as the excited relaxation occurs.
I would think that if it's a phonon-induced dissociation of that bond, then it would have also thermalized long before 30 nanoseconds. Those phonons will have dissipated, and
they will have dissipated. So you're right. It's a So I guess I would separate phonon. I would separate the effect of phonons. What am I trying to say? The effect that phonons have while they are excited versus sort of a not irreversible, but like you mentioned, like it's sort of a chemical change of bonding that takes some time to reform. That's triggered by the excitation of phonons or electronic perturbation.
Super interesting. And you sell the spectroscopy, the techniques basically to measure this, the spectroscopy setups to measure it. You now sell them.
Yes, we do.
So then I should keep that in mind for my next proposal. That could be very interesting. Although Monique can probably tell me now that she can do it. Thanks a lot for your answers. I think it's a super interesting talk, super interesting topic, and
thank you.
Lots of chemical insight here in what's happening on the surface.
I appreciate it.
More questions? Oh. I was wondering if you ever observed, because apparently it doesn't happen here, that the electron is actually transferred to the ligand. But did you ever, from an inorganic material, observe electron transfer to organics absorbed on it? Or is it very rare or hard to?
So yeah, with the right ligands that's been observed, they would typically be, I mean, so they would typically, well, their frontier orbitals would be more aligned with the electronic states of the nanocrystal. So those would be the larger conjugated systems, so that the pi star orbital, for example, would be aligned with the conduction level, or yeah. So these are all
observed it with mid-infrared light in this case. That was more my question.
Oh, well, we haven't. So I mean, we haven't. No, with these ligands, we haven't observed. I mean, I don't think we've observed that in these ligands, but I guess I say that because they're all, except for the, delocalized pi bond to the carboxylate, there's no energetically accessible states in the ligands.
Yeah. Because I find it also very intriguing that the ligand doesn't seem to matter, and then I would think that at some point there must be some ligand existing that will have an effect, right?
I would, yeah. I mean, I would imagine if you find so for example, ligands that have an effect. I'm thinking about some of the essentially inorganic ligands that I'm thinking about materials that Dmitry Tilapin has explored over the years, which, you know, are there's sort of these anionic chalcogenide ligands that create almost like a shell, a charged shell around the nanocrystals. And, you know, he demonstrated these extremely high conductivity, you know, transistors with such ligands. You're now having those types of a shell, but energetically close to the core, would likely have a much stronger interaction with the electronic states of the core. If you have ligands with frontier orbitals that are more energetically aligned with that of the nanocrystal, I would imagine you begin to have coupling, maybe even just from the electronic states of the ligands, which would probably involve changes in their vibrational features as well.
Mm-hmm. Yeah.
So
yeah.
I just remembered some old work by Philippe Guilloux-Nest. I think it probably started this whole discussion on how the Phonon bottleneck could be coupled to ligand vibrations.
Mm-hmm,
and he did show quite clearly that there were effects on the P2S cooling rate for different organic ligands. So that seems a bit at odds with your conclusion, and even my own conclusion that we've measured in the past for lead chalcocanides, where we didn't see much of an effect. But for calcitonite, he clearly showed quite strong variations.
Mm-hmm. Yes, that's right. So they were, you know, he would have these sort of hard soft types of explanations where the ligand chemistry, the ligand would essentially create surface states that were energetically close to the core states, if I recall that correctly.
I think you could explain it in terms of just near field energy transfer to the ligand vibration. So if there's a resonance between the, let's say, P2S transition and a ligand vibration, then of course you could couple.
Close in energy. Mm-hmm.
Yeah.
Mm-hmm.
So maybe that's not the case, maybe. But if it is the case, then you can probably get coupling.
Yeah, that's a good point.
Are there any further questions?
Hi, perhaps I have a question.
Yes, please, Guilherme.
Hi, thank you for the nice talk. My name is Guilherme. I'm a postdoc in Arjen's group, and yeah.
Hi.
I just had a question regarding the 1s to 1s line width. Does it change when you change the ligand?
Oh, the excitonic line width?
Yes.
Let me see now. I don't think it does actually. I mean, within the two that let me look to see if I happen to have the absorption spectra.
I mean, perhaps also from the TA spectra.
Can't tell well. It's two. Let me look at the transient spectra then. Let me look at. I'll just look at the oleate and the mercaptor propionic acid. Oh, of course, this is a transient. So we really ought to be looking. I don't have the just the electronic absorption spectra handy.
I would when you raise this question about the line width of the other orbital transitions.
Mm-hmm.
Well, then I also remember this work by, I believe, Vanessa Wood, where she shows that the line width of the exciton transition can be tuned to a certain extent by changing the ligands that you have on the surface.
Yes, yes.
So I was wondering if you would see a narrowing excitonic line width, if this would be then also correlated with the narrower line width for the
Yeah. So with this, I mean, with these particular ligand comparison, we don't see a big effect here. You're absolutely right. You can find ligand chemistries that do affect this, so their interactions. It'd be interesting to basically do the same kind of measurements on those nanocrystal ligand combinations to see if the results that we would find differ from these. I would say from this system, again, we really ought to be looking at the ground state absorption rather than the ground state bleach. But using that as a proxy, because I've got it handy in this presentation, I'm not seeing a big effect here.
Perhaps you tried those ligands, Arjen, in the past.
We were just thinking, if we removed the organic ligands, replaced it with inorganic ligands, surely the cooling should slow down, right? Because there's no modes in the organic ligands to accept the energy. But it wasn't so simple. We could never find a real trend or we didn't believe the effects we saw. The trick with these ligand chemistries, of course, is that it's very hard to know what you actually have on the surface.
Yes, right.
But Matt Beard knows what he's doing, so, and you probably do too. But that's very hard, right? You can try a ligand exchange procedure and then you can hope for changes. But what do you really change in your ligand exchange?
Right.
It's hard to know.
These ligand exchanges were done in the solid state in the film, which at least gives you more time. Right? You don't have to maintain solubility.
That's true.
Doing it in solution is very challenging to affect complete ligand exchange.
Okay. We went significantly over time. I think that's why a lot of people left the next thing in their agenda.
Yeah.
But it was a really great talk. I'm also thinking, as Arjen and Guilherme are also interested and Hannes listening in because he also does transient spectroscopy. I mean,